Okay, so without much further ado, I'd just like to welcome you to this workshop on advancing geophysical and astrophysical turbulence on behalf of me, Leray, who is about the lead, so thank you all for coming. This is part of the broader program on the mathematics of turbulence. Before we start, I'd just like to say that it's been about a year since our colleague and friend Charlie During passed away. Charlie was a great supporter and one of the organisers of the broader programme, and we do miss it. Okay, and hopefully you've all got the timetable. So we'll start without too much further ado. I'd like to welcome Emmanuel Dormy from ENS. Emmanuel is one of the world-leading experts on dynamo theory. He has a beautiful book, The Key Offer, that I'm sure he'll be happy to sign for you. And he's going to talk today about understanding the force balance in numerical models of the geodynamo.
Thank you very much, Steve. Thank you to the organizers for the invitation. I feel very privileged to be here in front of this audience and talk about the geodynamo. I would like to say two things before I start. The first one is that all the numerical developments, the recent numerical work that I'm going to present has been performed with Robert Teed, and actually is the one that has done the simulation and should get credit for that. And the second one is that I am in front of a mixed audience with some people in the room that are expert or have worked before on dynamo theory. A vast majority hasn't, I think. And so therefore, you'll have to bear with me for the first half of the talk. I will just recap what needs to be known in order to follow the research bit. And the second part will be research. So please bear with me for those of you that are familiar with the subject. So what we want to understand is the generation of the Earth's magnetic field in the Earth's core. So the Earth is a differentiated planet. The heavy elements are at the center. So it's mainly iron, and it's in liquid state until the pressure does more than compensate for the temperature increase, and it forms a crystal at the center. So there's a solid inner core and the liquid outer core, and this is conducting liquid metal, and it's believed that it's the motion of this conducting fluid inside the Earth, 3,000 kilometers under our feet, approximately, that generates the Earth's magnetic field. So if we want to write down a set of equations of PDEs in order to govern that, the simplest possible model we can think of is to look at an incompressible fluid. So we just take the Navier-Stokes equation in their incompressible limit and take into account the fact that the Earth is in global rotation. So we have a Coriolis force. Then we need something to sustain the motion, and that is convection. So we have an advection diffusion equation for some temperature or density difference, which relates to the flow or drives the flow through a buoyancy term. This is the so-called Boussinesq approximation, where we assume the fluid to be incompressible, except when it comes to the buoyancy term. Okay, and then it becomes an MHD problem. So in order to take into account the fact that there are electrical currents in the core, we also have an equation which governs the evolution of the magnetic field in the liquid, which is also a little bit of an advection diffusion equation, except that there is a stretching bit. It's a reminiscence here of the vorticity equation. It's very similar to it. It's called the induction equation. It governs the evolution of the field in a conducting liquid. And then the field will have an effect back on the flow through the Lorentz force, J cross B. So 1 over mu curl of B is the J term. Okay, so these are the governing equations, which we often rewrite in a non-dimensional form. And so these are the equations that I will be discussing today. So here, the unit of time has been chosen to be the magnetic diffusion time. So we have no non-dimensional term here. However, we have a non-dimensional terms here, a magnetic Ekman number. We have an Ekman number here and a modified Rayleigh number, not quite the definition that we usually use, but a normalization of the buoyancy by some other terms, which are the ones that balance or counteract the convection in this problem. Yes?
Supposed to be for there the G constant.
No. So inside, if it's a sphere of, so the question is whether gravity is constant inside of the Earth. Of course, it's not, because it's the liquid metal itself that does provide the gravity. If we assume that it's roughly uniform in density throughout the core, then gravity scales like R, and that's what's done here. So the gravity is R times this coefficient G that I have in the equation. So it's a sphere with uniform density. Okay. Please feel free to interrupt me if anything I say is unclear, unconvincing, or whatever. So the interesting thing is to look at the parameters for these the values, typical values in the Earth for those parameters. I didn't put the value for the Rayleigh number because in our thinking, it's really the knob that you want to turn in order to increase or decrease the driving. And it's quite hard to relate the Rayleigh number in a busyness model to the Rayleigh number in the Earth, which is not quite a busyness fluid. I mean, there are deviations. The fluid is stratified against its own weight. So an inelastic approximation may provide a finer model. Only we have so much trouble already with the busyness equation that we stick to that. Okay, so that the values are here, and they're extreme. They're extreme, which is on one hand a good news. It's a good news for applied mathematicians because we can do expansion, we can drop terms, try and get asymptotic limits. It's a bad news when it comes to doing numerics because numericists have a great deal of trouble having, for example, the viscosity low, because that's the term that regularizes the flow, and dropping it, I don't have to tell that in front of an audience, used to turbulence is not an easy thing. So there's a whole history of numerical models for this problem. I was working on that in my thesis from 94 to 97. And at the beginning of my thesis, there was a major setback. The problem was solved. It was solved by Gatmeyer and Roberts in UCLA. Paul was in UCLA. Gary was at Los Alamos. And they did a very heavy numerical model that made the cover of Nature at the time. And you can see that it was quite an important result. It's quite obvious judging the figure, the picture. The Ekman number was there 10 to the minus 6, quite a challenge, a difficult simulation to achieve. And they had something which looked like the Earth for the first time with dipolar field and even geometric reversals. The question, of course, was to try and understand whether this was really a model suitable for the Earth core, because the Ekman number here, the small parameter, was 10 to the minus 6, and it's 10 to the minus 15 or maybe 14 in the Earth core. Of course, everything I say has an error bar of maybe a coefficient 10 at most. Then, in a few years later, the group of Christensen, Olson, and Glatzmeyer used the same code, modified it. The main criticism was that it was using hyperviscosity, and they solved for the proper equation in the sense that the Laplacian, the viscous term, is a real viscous term in these models, and varied the parameter. And they said that you don't need to use that small in epsilon in order to achieve something that looks like the Earth. This is the Earth. Okay. So the idea was that this might be sufficient to get the limit of the Earth core. I'll make a long story short because I mean we have 30 years maybe of simulations, but those simulations are extremely expensive. They use the biggest computer we have, and it's always tempting to try and relate them to the Earth. And pretty much every year or every 2 years, a better model is published with a claim that we have now achieved something that is in the right limit. So that probably is the last one, 2021. You see that the Ekman number now is getting really small, very heavy simulation. This is using, again, a large eddy simulation. So they've got back to using a proxy for the viscous term because that's a way to decrease the Ekman number. So it's a higher power of the Laplacian that increases rapidly at small scale. Okay, as I said, that the fact that those parameters are a bit extreme is a good news for analytical work, asymptotics. And in fact, there's a whole series of papers that has been published over the year in which magnetoconvection has been done, because solving the full nonlinear problem using asymptotic techniques is not an easy thing, but magnetoconvection can be tackled. And there's a whole stream of paper that investigated what happened in the limit of very small viscosity, very small inertia, the two small parameters that we had. And what they did was introduce the Elsasser number, which is a way to measure the strength of the magnetic field compared to effects, other effects, essentially omega and eta, which are the two effects that are slowing down the growth of the field. It's a normalization of the field, if you like. The magnetic energy normalized. Think of it that way. And this is one of the, I just put the highlight on two results because they're important to understand what we're trying to achieve numerically. This is numerical simulations done by Fern on magnetoconvection. And what is shown using reduced model is that the critical value for the onset of convection had a minimum when the applied field was of order 1 in sense of the Elsasser number. So when the Elsasser number is reaching 1, it's much easier to drive motion in the models than without the field. And the reason is that the rapid rotation inhibits the convection and that the presence of the field can relax this inhibition. In other words, there can be a balance between Coriolis and Lorentz that allows for an easier driving of the motion. This pushed Paul Roberts in '78 to propose a bifurcation diagram like this for the Earth's core, which is a bifurcation diagram in which, as you increase the forcing and measure the strength of the field, think of it as the Elsasser number. I think that's what he means. He was probably missing a lambda and used an A. You first get a branch in which the strength of the field is controlled by viscosity, because something has to allow for motion, for starters. But then when the driving is strong enough, you relax to this branch, which is through a runaway field growth, which is a strong field branch in which the Elsasser number is of order 1. This is another paper. We published that in journals that are not very easy to find, so it took me several years to find the real original figure. But the idea is this, that the Elsasser number here will be order 1 on this branch. It's not 1 and a constant, but it's slowly varying. It stays close to 1. And here we have a weak field branch. Okay. One other bit of theory, and then I'll move to the numerical work, is the Taylor state. It's Brian Taylor published this wonderful paper in '63, J.B. Taylor, so not GI. The idea is the following: if you take the governing equation, the Navier-Stokes equation, and drop the small terms, if you're doing something which is a bit nasty, you're dropping the inertial term because the prefactor is small, 10 to minus 6 we said, or 10 minus 9, and we dropped the viscous term because the prefactor is small as well, 10 to minus 15. So this is something that's only valid at the large scale. Obviously, at small scales, either in time or in space, something different will happen and the small terms can reappear. But at leading order, at the large scale, you can look at this equation. It's an interesting equation because the U here does not follow a time evolution equation. It's given by this equation here. And the obvious thing to do when you have an equation like that is curl the equation. You get du dz on the left, and then you can integrate and find the U, given the B, which follows a time evolution equation. That's the so-called Taylor state, and it's the holy grail of this field in the sense that it's really something that people want to achieve and obtain a numerical solution for, but it's challenging. And you can ask yourself the question, that's what Brian Taylor did, under what condition an equation like that, where F here we gather buoyancy and Lorentz force, has a solution. And there is in fact a solvability constraint in that if you integrate over a cylinder like this, which is a geostrophic cylinder, then there should be no flux out of the cylinder because there is no flux out of the cap here, which are bounding the cylinder, which are solid. So there's no flux through the solid entering the mantle. So because there's no radial flux on the caps here, there must be no radial flux on the cylindrical radius here. Okay, and this implies that in order to have a solution in this problem, one needs to have that the integral over the cylinder of the phi component of F vanishes. This is known as Taylor constraint. If you don't have that, you can solve this problem. So you need to stay on a manifold where B evolving through the induction equation satisfies this constraint. Okay? It's very challenging, this. It's a very tough topic. I won't really discuss it because there are very few numerical results on this, but that's really what we should aim for, but it's extremely challenging to make progress here. Interesting thing to notice is that, of course, there is an element in the kernel here of this balance, which is the geostrophic flow. So on top of any solution, you can add a geostrophic flow, arbitrary. Okay, it won't change this balance. It's in the kernel of this equation for you. The geostrophic flow being a U phi independent of Z. So these are the geostrophic contours. Okay. Okay. And Taylor argues that this geostrophic flow is uniquely determined by these constraints being satisfied for all time. So the U phi function of Z, the geostrophic flow, which seems arbitrary here, is in fact determined by the fact that these constraints needs to be satisfied for all time. Okay. So just one last word on the Taylor state. So it's very hard to tackle numerically. If you want a starting point, you can look at this recent paper by the team of Andy Jackson at ETH, which highlights the progress and also the difficulties. And it's important to stress that it is a balance that only makes sense at the large scale, both in space and in time. By this, I mean that if you look at small scale, you will get boundary layers, shear layers, and they will be here present. And if you look at short times, there will be oscillations. And these are known in the Earth core as torsional oscillations. And I can suggest the following reference if you want to investigate or are interested in these. Any question on the asymptotics, or maybe we could keep questions for the end, or interrupt me whenever something isn't clear. Okay, so now I will summarize 30 years of numerics. So the numerics, these are the values estimated for the Earth core, orders of magnitude, and the numerics state of the art is in this sort of range. I told you that the Ekman number could get lower, but at the cost of changing the equations and having an LES model here. So not really solving this problem. Yes, Idris.
To the end, but you didn't say anything about boundary.
Ah.
So we dropped the Viscous, not that what about boundary?
It was a good idea to keep it. It was a very good idea to keep it to the end, Idris. So boundary conditions, if you look at the full problem, there should be no slip. That because the mantle is a solid, and that's the standard set of boundary conditions. If you drop the viscous term, obviously you just have impermeable boundary condition. That's all you need to get a solution to this problem. That's all Taylor used to get a solution for this problem. And just to finish on that, some people are using stress-free boundary conditions in the numerics in order to get rid of the boundary layers and achieve faster a balance which is independent of viscosity. Okay, thank you very much. So again, it's a brief summary, but so that you see where I'm coming from before I discuss the question of force balance, which is at stake at the moment in the community, and that's the thing that is being discussed. So this is a diagram which has been adapted, but you see it's quite old. 2002, republished, a little bit improved in 2006, and what they did was say, okay, we cannot just rely on one simulation, which is the best we can achieve. What we need to do is vary the parameters and try and understand what happens. So they did phase diagram for dynamos, and the phase diagram here are here you vary the ratio of the two small parameters, or PM if you like, if you're from the field. This is at the Ekman number smaller and smaller and smaller as you move to the right, and this is the forcing RA cubed divided by critical value of RA cubed. And what they found was that there are essentially regions in the parameter space when no dynamo can exist because the driving is not strong enough and the diffusion is too efficient on the magnetic field. And there are regions where you get dynamos, sometimes dipolar dynamos that are Earth-like. And if you push the driving, you get multipolar dynamos that are not quite as Earth-like. And the reason is that the inertial term becomes significant. And as I told you, it shouldn't in the Earth. So the question is whether those dynamos here relate to the geodynamo, and that's been discussed for years, and with very strong arguments of sometimes. This is one of the results that was published by Christensen and Aubert in 2006, and where they showed that, in fact, what was claimed by the theory was not quite right. The Elsasser number, as a function of the driving here, varies a lot throughout the simulations. So the expectation was that the Elsasser number would sit on something which is order 1 and not very much. And this is not at all what they observed. The explanation for this was put forward years later by King and Buffett. And it is to say that, in fact, the length scale of the flow in this dynamo is always very much dependent on the viscosity. It shouldn't if we were in the limit of very, very small viscosity. But here, everything scales like e to the 1/3 in the limit of a small Ekman number. So this highlights that these dynamos, in fact, are viscous. They are too viscous. One way to get rid of viscosity, and it's not in front of an audience trained turbulence that I will tell you this, if you increase the forcing, then you get the viscosity gets less and less important or acts at a smaller scale, but it's replaced by the inertial term, and it's not what we're after. It's a bit of a shame to say that in front of a turbulent community, but we were after a limit in which we can drop both viscosity and inertia, which is a very funny limit. That's the relevant one for the Earth. So what I suggested in 2016 was, instead of trying always to aim at the model that looks the best, and the model that looks the best in this parameter space plot sits here at the lowest possible value of PM, because PM is a small parameter for liquid metals. So we are essentially here. Maybe look at something which is a bit higher up and see what it gives. I did that by introducing a distinguished limit for this problem. So there are several small parameters in the problem, E and PM, for example, or E and E eta, the same thing. And I argued that maybe the most sensible way was to have one small epsilon tending to 0 and try to achieve the limit that way. I proposed then a scaling which would tend to the Earth in the limit of very small epsilon, but yet result in the fact that PM would be not so small in the numerical models as we're trying to do. And when I did that, so I'm looking in the parameter space up there. When I did that, I found another branch of dynamo, which is sitting here, which in fact coexist a little bit as in the Roberts diagram with the weak field branch. There is a region of the parameter space where you have a bistability, and you can get both branches. And I could relate that to bifurcation diagram like this. And so, in fact, I argued that most of the models are sitting in this region where you've got a continuous transition from something which is largely viscous at low forcing and inertial at large forcing, and that if you give more strength to the magnetic field, you can get into a region where you have a viscous balance for starters, but then you can relax that and get a balance in which the Lorentz force balances at large scale the Coriolis force, and both viscosity and inertia are essentially negligible. This idea of a distinguished limit took up, and in fact, numericists are now using it. They've changed the name. It's called the pass in the parameter space, but it's exactly the same idea. It's just having one parameter tending to 0, and you relate all your small parameters to powers of this parameter. Okay. But it took up, and that this is good in a way. And what I argued is that if that way I've managed to get this term small and this term small, then taking the curl of the equation, this drops. Taking the radial component of the term, this drops because this is purely radial, and I should get a balance between the radial component of the curl of these two. And in fact, this is what's observed in the numerics. This is the radial component of the curl of Coriolis on the left, the radial component of the curl of Lorentz on the right. And you see that this is a snapshot, this is a cross-section. If you don't like cross-section or think the angle was chosen so that it helps, this is the 3D. I don't think it helps much, the referee, so that the angle was chosen so that it works. So we did also a 3D plot. But so you see there are discrepancies, there are places where there are deviations, which are obviously effects of inertia or viscosity, but at large scale, the dominant balance is between those two terms, and they tend to balance pretty much everywhere, except for shear layers, except for places with rapid acceleration. It's not valid at all scale, of course, it's just a large scale balance. Okay, one last thing before I move to the new question that we're asking is if we're correct, and in fact, this term and this term is small, what controls the strength of the field should be this parameter here, RA tilde. And this is a figure we produced in 2018. And in this one, you see that the Elsasser number here, so this is the strength of the field as a function of forcing. If you look at the models that were published at moderate PM or small PM, then they they disperse quite a bit, showing that other parameters are important, the two epsilons. Whereas if you look at this large PM value up in the parameter space as I showed you, so this strong field branch, on this strong field branch, there is, of course, still a small dependence, but much weaker. So it seems that this RA tilde is the controlling parameter for the strength of the field. Okay. If there's no pressing question here, I will move to the question that I want to address now, which is an important one because it's one that is recurrent in our field, and currently it's been argued very strongly that it is met, and that we have met now in the numerical simulations the right force balance. So the idea again is that we're solving for a problem in this setup, that we have all these terms, and that we would like to have inertia and viscosity small, because they're extremely small, asymptotically small, if you look at the geodynamo values, the values relevant for the geodynamo. And all this is under the assumption that the divergence of the flow is zero, therefore the pressure can be as large as wanted in order to ensure this constraint. And the state of the art in the community at the moment is to argue for scale-dependent force balances. So there's been quite a lot of papers published on these scale-dependent force balances in JGI actually in the last 3 years, and they all argue that in fact looking at this large-scale force balance is not quite what needs to be done. Instead, what needs to be done is look at the scale dependence of the force balance. So this is not my figure. This is a figure from this latest paper in the list. What is being plotted here is the RMS value of each forces as a function of the spherical harmonic degree. So because all the simulations are in a sphere that I'm using spherical harmonics, so the L's that tells you the degree spherical harmonic, the L in the YLM gives you an idea of the typical length scale. So you get the RMS value of each force as a function of L, and you see how it evolves. Now we'll summarize what the argument in this paper is. The argument is that at leading order, if you look at the first terms, the dominant terms, the dominant forces, the balance is between Coriolis and pressure. So this would be the geostrophic balance, because it's not an exact geostrophic balance. The authors refer to that as the quasi-geostrophic balance. So it's leading order QG, quasi-geostrophic, because those two terms are in balance. And then you can take the Coriolis force, subtract the pressure, and you get the ageostrophic part of the Coriolis force, which is here in violet. And this one is in balance, depending on the scale, with the buoyancy force at large scale and the Lorentz force at small scale. That's what's being observed in the numerics. This is one of the plots. As I said, it's the state-of-the-art one with the hyperviscosity, but they do not differ that much for the other parameters. And the other terms, you see, inertia and viscosity are small. Success. So the problem is solved. We have a simulation where those two terms are small. So it's a QG at leading order, and the next order is a Mach balance between magnetic, the Lorentz force, Archimedean, the buoyancy force, and Coriolis, but the ageostrophic part of Coriolis. Okay. So this is argued to be the balance that is observed in the numerics. It's argued to be relevant to the score. It's not quite what I discussed before, but it's clear that inertia and viscosity are small in this graph. Okay, and the crossing here, L perp, between the Lorentz force and the buoyancy force is thought to be quite important because, according to what is the interpretation that is made, is that this crossing is really the scale at which the energy flows from the buoyancy to the magnetic field, at which the dynamo is generated, the injection length scale for the magnetic field. Okay, so that's what is being published, and I will try to question that. So yeah, before I question that, is everything I said clear? So the idea is that in the numerics, the best numerics we have, very heavy, very expensive, we achieve QG at the large scale, as the dominant balance, at the dominant balance, and the next order is Mach between magnetic field, buoyancy, and the ageostrophic part of Coriolis. So it's called QG Mach, yes?
So is the reference edge, is that the cutoff of resolution, or resolution goes further?
It goes a bit further. It goes a little bit further. I think. But you have to bear in mind that this is not a viscous term in the sense of a Laplacian. It's a higher power. It's an LES simulation. This one. So the very steep increase is probably due to, it is due to that. Okay, but that's a way to achieve at large scale a lower viscous term. Whereas in other models which are not quite as state of the art as this one, those two curves would be larger. We'll see some of these, but the general picture would remain the same. It's just a question of how much gap we have here.
I just wanted to pick up on what you just said. So in quasi-geostrophic theory, you have leaning on geostrophic balance, and then you have a geostrophic flow which you can compute, which maintains that balance against forcing. And so I assume here that was sort of equivalent to that equation, which now the forcing is now Lorentz plus buoyancy and lead rate. So the whole thing is like QG at the top.
Yes, except Lorentz would not really in general act as a forcing. It's more a sink of energy, but it's QG, exactly, yeah, that's the picture that they have in mind.
So you're maintaining a primary balance against forcing by these two possible forces, buoyancy and magnetic field.
Yes, exactly. Yes, yeah, exactly. Okay, so I will try to challenge that, and then we can vote at the end and decide whether there's something to be discussed or not. Maybe I'm wrong, but I will challenge that on the basis that again we have a divergence-free flow. The pressure can be as large as we like. It's balancing the pressure part, the gradient part of all forces in order that the sum of everything is non-divergent. And since we're in Cambridge, I will refer to Bachelor. And it's well known that in this limit, it's a sensible thing to do to take the curl of the equation. And when you take the curl of the equation, you end up with an equation for vorticity, which gets you rid of this pressure problem, and you don't have to worry about it anymore. In fact, the codes that are being used for this simulation, I wrote the code during my thesis, so I know it well. It's exactly that, done that way. It's taking curls of the magnetic field. So it's the poloidal toroidal decomposition. So you expand the field in terms of curl, and curl of potentials. And so it's exactly doing this. It's solving the curl of the equation. Okay, but you can reconstruct a posteriori everything. Now, in order to get you into my thinking, I will introduce the Leray projector. It's important to think of it because it will probably shed light on what I mean by what needs to be done. So the Navier-Stokes equation you can write like that, but you can also rewrite it by saying that this is the projection, the Leray projector, of all the terms except pressure. And the Leray projector is just a projector on the divergence-free space, solving this Poisson equation with the divergence of B. Okay, and you need in an open domain like the Earth core, you need a boundary condition, and what you ask for is that the projected value has no normal component. That's the standard thing to do. This is driven by the fact that the vector field, any vector field W, can be uniquely decomposed in a bounded domain with smooth boundaries in a pure gradient flow and a divergence-free vector. If you don't specify the boundary, you run into a problem. If you don't specify this boundary condition here, you run into a problem with the harmonic field. I'm looking at Idris, who's with me on this one. It's good. Okay, and so of course this boundary is well suited here because we know that the flow shouldn't enter the mantle. There's a boundary there, so there should be no flux through the boundary. So this is a good choice of boundary condition. It's quite hard to see what the boundary conditions would be on each force individually. In fact, there's no rationale to decide on that because we know what the boundary conditions are on the force. We have no physical boundary condition on the divergence-free part of each force. And what I argue is that in the graphs, as the one we've seen, we're comparing largely gradient terms. So the thinking here is that because the Coriolis force and the pressure are the dominant force, it makes a lot of sense to subtract the pressure gradient from the Coriolis force. But this ageostrophic Coriolis is not divergent-free because the pressure here in the simulation reacts to all the forces wanting to cause divergence. Okay, so this pressure should in fact be splitted into one part, which is the dominant one, which balances Coriolis. But there are other parts of the pressure gradient which are here to ensure that the Lorentz force does not cause any divergence, buoyancy, and so on. Yeah. So in fact, here we're talking about dynamics because we look at crossing between forces, and then we argue that this is the injection length scale for the energy magnetic field. So we really discuss dynamics, but we're comparing gradient terms, which is, I think, a first order mistake in incompressible, with incompressible fluids. And so what I argue is that it's better to take the curl of the equation. Okay, we could want to uncurl. Well, let's first show you an example. This is an example of a simulation that Rob has performed. Man number 10⁻⁵, PM1, and the real number is 10 times critical. And that tells you, you see, it's not quite as good in the sense of having those two forces small, but it's not bad. You get the same idea that you have this large scale balance between Coriolis and pressure, and that if you form the A geostrophic, it's balancing those two which cross here at L perp, and that the other ones could be argued to be small, not quite as small because it's a much lighter simulation. So this is the sort of picture that we would get. Now, if we take the curl of the forces and compare curl of forces instead of comparing forces, we get a completely different picture. So now here, everything is gradient free. We're really looking at things that act on the dynamics. Well, first of all, you see that here those three curves are very close to each other. There's no pressure, obviously. Those two curves are small, but not quite as small as before. And the crossing is A, not so well defined, and B, not at the same length scale. Okay. So if you look at curl of forces, the reason why people don't like that, I've understood that from discussions in seminar and presentation, is that taking the curls gives you a spectrum that increases at small scale. You're giving a lot of importance to the small scale, of course, you're taking a curl. Okay. So what I argue for is that we can easily, now that this was true in the 2016 paper where I was showing force balances, I took the curl, and it's true that I was highlighting the small scale. But now that we look at spectra, because we've got an L here, we can easily compensate for that. Okay, so it's not an uncurl. We're not integrating. We're not worried about the harmonic term that needs to be added if you uncurl, if you properly integrate. But you just compensate for the increase with K, if you like, which is L in our case because it's spherical harmonic, by just saying that the double curl of a vector which is divergent free will be the Laplacian up to a minus sign, and that the Laplacian throws an LL plus 1. So it makes sense to compensate for the curl with a square root of LL plus 1, which is very close to L, which is very close to K in Fourier. Yes.
Sorry to interrupt again, but this question really fits very well with where you are, and you'll change the tack a bit. Now, in the atmosphere, the hydrostatic constraint on the pressure is actually much stronger than the geostrophic constraint. I don't see anything analogous to that. I don't think there's any analogy of that here, but it's very dangerous to, in large-scale atmospheric flow, to get rid of the pressure in the way you've just done. You suddenly lose the fact that the pressure is not free to be set arbitrarily. It depends very much on the temperature field, which is a conserved quantity. Therefore, it's extremely strongly constrained.
Yes, it's a little bit of a, however, it's a little bit of a different, I mean, the atmosphere, the incompressible models of the atmosphere have a limitation. There's always this question of potential. Everything need to bring back everything to the same height in order to compare because of the stratification, which we don't have in this problem at all.
Do you have any equivalent constraint? Some that has to know about the buoyancy term, know about the buoyancy term, and maybe the magnetic field as well. In other words, you can't, if you hide the pressure gradient term by taking the curl, you suddenly think the pressure can just adjust to whatever it likes. You can't do that in large-scale atmosphere.
Okay. I'm with you. So the short answer is we can do that in numerical models because those numerical models are incompressible at all scales. So the pressure gradient, in fact, really does that. It does exactly that. It does balance everything that wants to cause divergence. The question of whether this is the case in the Earth core is another one. Okay, but in the numerical models, we can do that. But maybe we can come back to that. I'll just, I don't have that many slides, so we will have time for a discussion on that. Okay, so this, again, this was taking the curl. And so you see that there's an increase at small scale. If you now just compensate for the square root of LL plus 1, you get a spectrum which is just a compensated spectrum of the curl of forces, so that it behaves a bit nicer and doesn't put too much emphasis on the small scale. But you see that it tells you something different than looking straight at the force balances. Okay, and you get this, that the three terms are roughly at equilibrium. The crossing is not quite at the same place, and the two other terms are small, but ish at the small scale. Okay, just to try and wind you up on this, here is another example. That's an example here where we look at forces in the numerics, and where we look at the compensated spectrum for the curl of forces here. Stunning, isn't it? So you see in this one, you can argue very convincingly that the viscosity here is negligible, whereas here it's the leading balance between viscosity and Coriolis. And the reason is twofold. First, there's no Lorentz force in this one, it's a purely hydro run. And the second one is that in this plot here, we integrate, we take the RMS value of the forces, including here the boundary layers. That's not what we do usually. What we do usually is drop the boundary layers. But that's to highlight the danger of discarding one term based on that, where in fact it can be a leading order term. So in the previous plot that I've shown, which was the dynamo, I discarded boundary layers, and from now on all plots except for the two I've shown, it's without boundary layers. If you do that without the boundary layers, you see that not very surprising, the viscous term drops because it's essentially important in boundary layers. And if you look at the curl, you now have a viscosity which is small up to a certain point, then enters the leading order balance, which does not appear here. And you get inertia being slightly less and kicking up larger. So that's at 10 times critical for an Ekman number of 10 to the minus 4. So you see that the picture changes a lot if you look at the force balance, deciding to group pressure with Coriolis, and then looking at all the other terms, and you're comparing terms which have a pressure force and therefore will not act, a gradient part, all terms have a gradient part, which does not act on the dynamics. So you can't say anything like this crossing is important for dynamics because you're adding on top of each forces a gradient part. Okay, whereas here we're free of this gradient part problem, and therefore we can start discussing effects on the flow. I'll show you here one last example, which is again, you have to appreciate that these are Ekman numbers that are not that small, so it's not state-of-the-art heavy numerics. It's heavy numerics, but not the best simulation you can do, and you can just do one. You can vary parameters a little bit. This is if we take the usual representation for PM equal 1, which I argued before was a weak field branch, and PM equal 12, which I argued before was a strong field branch. If you look at it from the point of view of forces, in both cases you get this leading order balance here, which is the geostrophic one. And then if you take the ageostrophic flow, it does in fact balance buoyancy and Lorentz, and there is a crossing. So in both cases we're fine. In this one, maybe inertia kicks in a little bit too much here, but viscosity remains small. And in this one, they're both small. So we could argue, based on this force balance, that they're both equivalent and doing the same. Whereas, in terms of branches, one is on the weak field branch, the other one is on the strong field branch. So quite a different force balance at the large scale. If you now look at the compensated spectra for the curl of forces, you get a completely different story. So the dominant balance here will be between Coriolis and buoyancy, and the Lorentz force will come slower, nearly at all scales. And the two terms here, inertia and viscosity, which should be small, are small, but not all the way through as it did before, and they are indeed balancing. And that's important. We know that if we want to know at which scale the viscosity kicks in, we need to curl the equation. Otherwise, we underestimate viscosity. That boils, I think the message boils into that. If we now look at the curl for this large PM, which I argued was the relevant limit for the Earth core, or the relevant things that we should do in the current numerics in order to get geodynamo-like simulations, we get at leading order at the large scale a balance between the two, a Mach balance, Okay, so which is the Taylor, an approximation. It's not Taylor state, but it's this idea of the magnetostrophic balance. And the two forces, viscosity and inertia, are smaller, essentially at all scales. Of course, at the small scale, viscosity kicks in and regularizes the solution. So I argue that, but I can discuss this further with Mike, that we can have a long conversation, that looking at this is misleading. Looking at the forces straight is misleading, because if you're interested in dynamics, because a large part of all those curves are gradient terms, don't enter the dynamics. You have to appreciate that we have no direct observation measurements or whatever in the Earth's core of pressure. It's not at all like the atmosphere. So we rely on numerics, which is exactly incompressible. It's Boussinesque. So it doesn't affect the flow in the numerics at all, the gradient part. And if we curl the equation, we get a completely different picture in which we can distinguish between the two limits and argue that if PM is large enough for a fixed Ekman number, so this distinguished limit I was pushing, the balance at the large scale is a magnetostrophic one relevant to the Earth's core. Now, it's only at the large scale, it's only an approximation, viscosity cannot be dropped at all scale. It's not the Earth, it's approaching. So I'll end up here with some take-home messages. So if you're not working directly in dynamo theory, I guess what I would like to pass as a message is that the numerical models are getting better, that they are more and more impressive using heavy simulations, huge resolution, but that the way they are presented is not completely innocent, and that in some cases, the graphs that we have tend to underestimate viscosity in these models and the effect of viscosity on the dynamics. And that the force balance can in fact be only approached, not achieved, if we use the right distinguished limit. Meaning, if we take the right starting point for the pass and the right exponent. So in other words, if we have just one small coefficient and we follow the path of the distinguished limit, starting from a dynamo which is not in the right balance, following this path, we will stay on dynamos that are not in the right balance. If you work in dynamo theory, the take-home message would be take the curl. That would be it seems simple, but I think it needs to be done. And that's because I think the gradient terms are misleading when comparing forces in the spectrum. And that in fact, having a pass-through parameter or a distinguished limit, I don't mind the way people like to call it, is not all. The thing that does matter is what the exponents are, what the starting point of this path is. And if we start with a dynamo which is not in the right balance for starters, it's not because epsilon gets small that it will necessarily improve. And I will finish by first thanking again the organizers for the invitation and say that if you enjoy Cambridge and the Isaac Newton Institute and you're interested in dynamo theory, there's a program starting in September, which I'm co-organizing on this. And I don't think it's a good idea for organizer to speak. So I am really very, very grateful to have been given the chance to speak in this workshop. Thank you very much.
Thank you, Emmanuel. A useful talk and for keeping the time. We do have time for lots of questions. So if you have a question, please raise your hand and Laura will come round with the next question.
Hi, general question. How much do we know from measurements of all this?
So in situ measurements, not much. There's no way we've been that deep, 3,000 kilometers. But we have surface measurements through observatories of the magnetic field. The mantle is reasonably good insulator, so we can downward prolongate the magnetic field. That's what, in fact, Carl Friedrich Gauss introduced for Ecole harmonics for this problem originally. So he was really interested in that. So we can do just that potential theory and get sensible measurements at the surface of the core. We have no measurement inside. From this evolution in time of the field, we have pretty good measurements. We can try and infer on a short time scale the motion at the surface again. And then from high pressure physics and everything, we have ideas of the coefficients, of the viscosity of liquid metal at such temperatures and pressure, this sort of thing. But everything is very indirect, as opposed to the atmosphere.
So those quantities are average, the viscosity and things like that you get. Average values?
It's not expected to depend much. I mean, the thing that would depend would be density, because it's very heavy. So even though it's liquid metal, it does compress a little bit on its own weight. So it would be a little bit denser, and that's why an inelastic model is sometimes used. I'm not aware that viscosity is said to vary a lot with radius. I don't think so. It's very small anyway. It's a very small term. So even if you change it by a small factor, it's not going to change.
Yeah, I have a question. When you first showed the picture about where the balance is at the larger scales, when you projected on spherical harmonics, now when you took the mean root,
This one?
yeah, now the average was done in time and in radial direction as well.
Yes.
So radial large scales do not count somehow. I mean,
very true. That's why you see when I did this correction of the spectrum, compensation of the spectrum with a square root of LL+1, it's taking into account only the horizontal length scale. And the spectrum has the same default. It's only the horizontal length scale that counts. The radial one doesn't. It's not that the small length scale are not there, they've not been dropped, except for the boundary layers that have been dropped in the integration, but they are spread through all values of L. The only thing the only ranking that we have here is L, the spherical harmonic degree. Yes.
Hi, thank you very much. I wanted to ask about your recent numerical work, Robert Teed. And did you also use, you said this work of Aubert and Gillet was performed using LES simulations. How did you perform your simulations?
Okay, so I don't, yes, okay. So thank you very much for this question. Where is it? So that's the set of work. In this set of work, only the penultimate one here uses LES. The others are genuine Navier-Stokes simulation. Okay, so they're not all using LES. Our simulations are genuine Navier-Stokes. We didn't use LES. But this one, if you like, is the sort of I would summarize it by saying it's the same sort of spirit as Gatzmeier and Robert. You're trying to do your best shot. You're trying to put everything you have in terms of computational power, get to the regime that nobody can get to, and try and get flamboyant simulation. And so then you have to accept things like LES.
Hi, I'm Robert Klein. I would like to get back to Edris's question with the radius. Now, if you do what you do, namely only count the mode number in the horizontal,
yes,
wouldn't you expect in the radial to pass through several regimes of anisotropy? Wouldn't you expect sort of different regimes depending on where you are in the particle?
Yeah. Okay, so first of all, it's not at all, as you said, it's not an isotropic problem in any sense. So if you want to think of the small scale, for example, you will have the effect of the large scale field. The field diffuses a lot, so it's rather large scale in the Earth's core. That provides a direction of anisotropy, which varies from one place to another. And then the rotation also tries to enforce that the fluid is as independent as possible in the direction of the axis of rotation. Therefore, it's also a direction of anisotropy. So at the small scale, you'll have two directions. Some studies, Martin Simpia suggested years ago, pancakes, where the structure would be elongated in those two directions, and you would essentially get diffusion through Taylor diffusion in the orthogonal direction. So yes, everything is anisotropic, and we don't measure this. It's you need to find a simple way to represent things. So I was at first looking at the force balance in space. If you want to introduce scale, you use one scale, and people used spherical harmonic degree, which makes sense because it's the L that's important for the length scale, not the M. So as far as the order is concerned, that's fine. As far as the radial direction is concerned, we're dropping it. We're assuming that somehow this is a good measure of the scale of the structures. But and this does not only apply to the very latest result I showed. It applies to this whole stream of papers that were. But I think it's what can you do? I mean, otherwise you have a 2D spectrum, you need to Fourier or transform using polynomials in radius and so on. This code, which I wrote, is finite differences in radius. So that's another reason why it's.
Maybe I can ask the last question then. You said something I'm not certain I quite agree with, but I think you were quoting something, but I think that's okay. But you said that L perp is. You said that L perp is where the scale on which you thought dynamo action, or they thought dynamo action might set in. But you can only understand where dynamo action sets in by looking at the induction equation, really. And this is all from the momentum equation. So does anybody ever work out a spectrum of U dot J cross B?
Well,
Which is
if
the
you
work done
integrate
by
by
Valence
part and assume that the boundary condition work well, you're going to get the same thing as if you, yeah, exactly. It's U dot J cross B, which is the same thing as B dot U.
Yeah. So does anybody work that out?
I don't think so. I think that's the idea in this crossing, that they argue that the Lorentz force will be a good measure for that. And that, but
Well, it depends on you.
I fully agree.
Okay.
Okay.
Yeah,
I think one of my, as I said, yeah, you're quite right in saying that this is a quote. I don't believe that this crossing is very important, in particular because it's crossing between gradient terms.
Yeah.
And so, and this is does not occur if you look at the curl. Now, of course, if you look at the curl, maybe one thing I should say is that because this is in the kernel, that's the geostrophic balance, it drops, it has to drop. Because it doesn't mean it's not there. It's the part we don't see by taking the curl. But then we need to think again of the Taylor constraint and the fact that Taylor explained that in fact this geostrophic flow U is uniquely determined by the fact that the Taylor constraint needs to apply at all time scale. There will be a geostrophic flow, but it's constrained, it's set. It cannot do whatever it's likes.
Okay, thank you. Oh, Idris, back for more.
No, this is a problem. No, this is a problem if you want to do numeric solving the curl. If you want to write an equation for omega and solve the equation for omega, it's a problem. The usual version is to introduce the stream function and do the stream function. It's exactly what we're doing in the numerics. We take the curl, we introduce poloidal and toroidal components, and we have the boundary conditions for them. They derive from the physical boundary condition. There's no trick there. And what we do here is take the curl of the forces once they're computed. So this is fine because we have boundary conditions on everything here. But you're right that integrating the vorticity equation causes a problem like this. Yes. Yeah. Well, that's what we do. That's what's being done in those codes. So the poloidal scalar has a bi-Laplacian as opposed to a Laplacian, exactly. And we have one more boundary condition there because you start from a velocity field which has 3 components, you go to 2 potentials, poloidal and toroidal. And so you have 2 conditions on the poloidal. Yes.
Okay. So on that note, thank you.
Thank you.